Abundant life. It's the hallmark of our planet. But it's water that makes us unique.
Liquid water is the essential environmental requirement for life on Earth. So when we look for life elsewhere, we start first by looking for liquid water.
Our search has taken us to an alien world that seems to defy the laws of physics. A place where water can't exist, but shows us evidence that it might.
We have what we in science call an anomaly.
NASA's Phoenix lander will find out if life is possible on this desert planet. Welcome to Mars, the water world.
Load relief kick rate is in, vehicles responding. Vehicles recovering very nicely from the liftoff transients.
August 4th, 2007 at 5:26 a.m. This Delta II rocket blasts off from Cape Canaveral. In its nose cone is NASA's first robotic Mars scout, the Phoenix lander.
At this point, we have a strong signal from Phoenix via Odyssey.
At NASA's Jet Propulsion Laboratory in Pasadena, California, engineers monitor the progress of the $500 million mission.
All stations, we have confirmed crew stage separation and UHF signal acquisition via Odyssey. Atmospheric entry on my mark. 3, 2, 1, mark.
The new generation lander enters the final phase of its 400 million-mile journey to Mars.
1 minute since LOS, standing by for signal reacquisition.
Phoenix will search the Arctic plains of Mars for the building blocks of life, including carbon, nitrogen, and most importantly, water.
Touchdown detected. Landing sequence initiated.
Phoenix intends to prove that life on Mars is, or was, possible. If it does, then life on Earth is not unique. This is a test simulation, but on May 25th, 2008, the team at JPL attempts this for real.
Primary objective of Phoenix is to explore the Martian Arctic and to determine whether or not conditions for life are there today or existed in the past.
If Phoenix finds what it's looking for, it will change our understanding of the solar system. If there's life on another world, it could mean that the universe is teeming with it, that the aliens of our science fiction could be a reality. Phoenix might even find them. But finding the signs of life on a planet millions of miles from home is an incredibly difficult challenge. The lander hasn't been designed to find life directly. It's been built to find the necessary ingredient for it: water. Chris McKay is a planetary scientist at NASA's Ames Research Center.
When we look at life on Earth, we see an enormous diversity. Organisms that do all sorts of different chemistry, live in all sorts of different environments. But the one thing that all organisms on Earth have in common is a requirement for liquid water. So naturally, when we look for life elsewhere, we start first by looking for environments that have liquid water.
Here on Earth, wherever there's water, there's life. Even in temperatures as extreme as 14 degrees Fahrenheit, organisms can survive. So if we find signs of water on Mars, we might find life too. But why are we looking on Mars? Professor of Geomorphology Vic Baker explains.
30 years ago, a spacecraft called Mariner 9 produced about 9,000 pictures, many of which showed large channels and valleys. And it was very obvious that these channels and valleys are directly analogous to what we see on the Earth, formed by water.
Scientists are stumped by these images. It definitely looks like water erosion, but as far as they know, there is no water on Mars. Its atmosphere is too thin to support it. The air pressure on Mars is less than 1/100th of the Earth's, which means the air on Mars's surface is the same as it is here on Earth at 110,000 feet above sea level. That's 20 miles high, nearly 4 times the height of Mount Everest. Scott Rafkin is a planetary atmosphere specialist at the Southwest Research Institute in Boulder, Colorado.
It's fairly common knowledge that if one goes camping or hiking and you go up to higher altitudes and you go to boil your water, as you go higher up, it boils at lower and lower temperatures. That change in altitude is what you're really doing is changing pressure. As you go up in altitude, the pressure is becoming less and less. And so what happens is that as you go higher up, it becomes easier to boil water. You don't need to raise its temperature as much.
This experiment shows the effects of Mars's atmospheric conditions on water. Gradually removing air from the chamber reduces the pressure. At first, nothing happens. But when the pressure drops to the equivalent of Mars's atmosphere, the water boils. Water normally boils at 212 degrees Fahrenheit, but at this low pressure, it boils at room temperature. On Mars, this happens at just 50 degrees.
The stability of water on any planet is tied to primarily the pressure. And the pressure on Mars is so low that if one could have liquid water sitting out on the surface, it would simply boil.
Mars's ultra-thin atmosphere creates another problem for water to exist here. There's not enough of it surrounding the planet to insulate it. Mars is ice cold. At its warmest, it's just 70 degrees Fahrenheit. At its coldest, the temperature drops to -225.
Now, of course, on Mars, we have another problem, which is that it's very, very, very cold. So even if one had the higher pressure so that the water wouldn't boil off, it would just freeze solid, like a rock.
The existence of these channels and valleys that appear water-carved baffles scientists.
The question is, how do you have these two things? How do you have a planet that is cold and dry with a thin atmosphere, and yet clearly, in its past, had flowing water?
Over the years, scientists have offered many theories to explain the features seen on Mars's surface.
People have suggested, well, maybe it's carbon dioxide liquid, or maybe it's lava, or maybe it's wind. Well, wind, lava, carbon dioxide could have formed many of the features we see on Mars, but they can't explain all the features.
And for the past 30 years, this has been the major source of science controversy. And it's the reason that the current NASA program is sort of directed with this euphemism, follow the water.
Using the latest science provided by Phoenix, NASA hopes to prove once and for all that they were made by liquid water, a substance that shouldn't exist on the planet. But the debate is growing more controversial. In June 2000, scientists got very excited about these images taken by the Mars Orbiter camera, a probe that has been circling the red planet since 1997. This one was taken in 1999, and this is of the same location in 2000. The images clearly reveal a changing landscape. To geologists like Vic Baker, these recently formed features look strangely familiar.
On Earth, we would call them gullies. They're sort of on the scale of hundreds of meters, no more than a kilometer. They're patterns like the veins in a leaf or branches in a tree that result from how water falling on the surface organizes itself into larger and larger drainages.
These gullies and alcoves seem to have been recently formed by water. They have appeared in the southern hemisphere of the planet, on slopes that get the least amount of sunlight during each day, one of the coldest parts of Mars. Their similarities to gullies formed by water here on Earth defy logic and the laws of physics. So what created them? Did water flow across Mars in its past? And is it still flowing today? On May 25th, the Phoenix lander, NASA's $420 million mission to Mars, touches down on the red planet to answer two questions that have vexed scientists for decades. Is there water, and could there be life? At the heart of this debate lies this rock that landed on Earth from Mars. Discovered in 1984 in the Antarctic, it's 6 inches long and weighs over 4 pounds. It's called the Allen Hills meteorite, and it's one of just 34 Martian rocks that have been found here on Earth. Johnson Space Center astrobiologist Dr. David McKay has studied this meteorite for more than 10 years.
Allen Hills is unique among the Mars meteorites because it's so old. It is by far the oldest of the known Mars meteorites. And furthermore, with an age of 4.5 billion, it is older than any rock ever found on the Earth.
McKay believes it contains proof life was possible on Mars. Using high-resolution scanning electron microscopes, he examines the meteorite and discovers tiny globules of iron and magnesium carbonate. Elements almost certainly formed and deposited by liquid water.
Carbonates are significant because they show that not only was water there, but it was relatively low temperature.
McKay is convinced that this proves Mars's atmosphere was once very different and could sustain flowing water, so the conditions for life were present. By radioisotope dating the carbonate globules, McKay comes up with a figure. Water flowed on Mars 3.9 billion years ago. NASA's current crop of rovers scouring the planet backs up McKay's findings. This is Meridiani Planum, the landing site of the rover Opportunity in January 2004. It's a dusty area the size of Oklahoma. Photographs relayed back to Earth reveal the soil is littered with countless BB-sized rocks. NASA scientists nickname these puzzling objects blueberries. On Earth, similar deposits form, but only in standing water or hot springs. Geologists have uncovered blueberry-like clusters dating back millions of years in Lake Superior and near the hot springs of Yellowstone National Park. Their discovery on the vast plain of Meridiani Planum suggests this area was once saturated with water, or was even an ancient lake. In fact, closer examination of the surface of the planet reveals that much of it was once a water world. These images, taken by a high-resolution stereo camera aboard the Mars Express spacecraft, reveal Mars's watery, almost Earth-like past. This is a large depression called Ioni Chaos, and next to it an outflow channel called Aris Vallis. They're the remains of Martian river systems, and to planetary geologists like Jim Rice, clear evidence of ancient catastrophic floods.
We took every river on Earth and put it in one spot, had them flowing at the same time. Some of these flood channels on Mars, when they were in full force, are 20 or 30 times bigger than those.
What was it that happened in the Martian past? Why do we have a planet today that is very cold and dry and gives every indication that we don't have liquid operating on its surface? Why in the past did we form these channels?
If Phoenix can figure out if water flowed across the surface of Mars in the past, it will explain the valleys and canyons we see today, and take us one step closer to discovering if water still exists, and even life. Now the Phoenix mission can confirm what the experts suspect.
It must have been warmer, at least for some period of time, so that we could have liquid water on the surface. And the pressure must have been higher than it is now, or the water would have boiled away.
Early in its evolution, Mars was much warmer. In fact, it was boiling. $4.6 billion years ago, our sun bursts into life and our solar system forms around it. Both Earth and Mars are huge balls of lava, boiling at over 12,000 degrees. Slowly, they begin to cool. Dr. Peter Smith heads up the Phoenix mission from its base at the University of Arizona.
Earth and Mars formed at about the same time, but Mars is only half the diameter of the Earth, and therefore it would cool more rapidly.
Mars's size proves to be the crucial factor in its transition from a fiery molten ball into a warm and wet planet. In this demonstration, two globes are used to represent Mars and our own planet, Earth. These scale models exactly replicate the difference in size of the two planets. Mars, shown here on the left, has half the diameter of Earth. Both spheres have been heated to the same temperature. Now they are cooling naturally. Infrared time-lapse clearly shows how quickly the smaller sphere representing Mars cools. Mars was cool enough for water at a time when Earth was still a red-hot ball. This water comes from comets. The early solar system is littered with large asteroids and comets made up of ice. As they crash into the planets, the ice melts. On super-hot Earth, the water boils away instantly. But Mars is cool enough to hold on to the huge quantities of water released by impacts.
And in that cooling, liquid water would be stable on the surface long before it would be stable on the Earth. And so during that period, it may be that you had rains and valley systems and lakes and all kinds of Earth-like situations.
Scientists believe that 3.9 billion years ago, Mars had the climate and atmospheric conditions to support liquid water, an essential ingredient for life.
Now, in the early days of the history of our solar system, this planet, the Earth, was not a good place for life to develop. We had noxious gases all over the places, volcanoes belching out all sorts of stuff. Mars was warm and wet and wonderful. It was the most likely place for life to develop.
Today, Mars is no longer warm, but is it wet? Understanding what happened to Mars's water is the primary goal of the Phoenix mission. Its success might hold the key to answering a 30-year-old question. Does water still exist on Mars? Scientists are now certain that Mars was once warm and wet. Pictures of ancient riverbeds, blueberries on the surface, and carbonate globules inside the Allen Hills meteorite confirm this view. But if there was water billions of years ago, where is it today? The question of whether water still exists on Mars will only be settled when NASA physically finds it. And that's the job of the Phoenix lander. It's being sent further north than any previous mission, to a site chosen because frozen water might sit below the surface. In 2003, NASA's Odyssey orbiter produces this image. Using its gamma-ray spectrometer, the spacecraft maps levels of hydrogen in the upper 3 feet of Mars's surface. Since high levels of hydrogen indicate the presence of frozen water, scientists think that these blue and violet areas, the densest concentration of the element, reveal an enormous frozen reservoir.
In fact, there's so much water in the polar areas and the nearby ice terrains that if you spread that water around the surface of Mars, that alone would inundate the surface of Mars on the order of 6, maybe 10 meters deep.
Phoenix's first job is to confirm that the hydrogen-rich area is in fact made up of water. Then scientists can begin to piece together the chain of events that lock the water under the planet's surface. Maybe then they'll begin to understand how the recent wet spots appeared. Some scientists believe they are a remnant of ancient climate change. Mars cools much more quickly than Earth, allowing water to exist on its surface. But a drastic shift in atmospheric conditions means it can't hold on to it. Earth's large molten core generates a magnetic field which protects our atmosphere from solar radiation. But Mars's small core cools so much that it no longer produces an effective shield. Solar wind blasts away its atmosphere and most of its water. Pressure falls and the temperature plummets. Whatever water it has boils away or freezes solid, leaving the Mars we see today, a frozen world. Up until recently, scientists believed that Mars's core is so cold that it is no longer able to crack and move the planet's surface.
The Earth releases a lot of its heat continuously by a process that's known as plate tectonics, where the continental masses of the planet are actually shifted by the formation of new crust in the ocean basins. Mars doesn't have that.
But the discovery of the gully features, the wet spots, suggests that Mars's core hasn't cooled as much as they thought.
Because it can't release its heat as efficiently as Earth, one idea is that this heat builds up with time, and episodically there's kind of a burst of heat release that will melt the ice in the Martian permafrost. And that water comes onto the surface, perhaps associated with gases that change the composition of the Martian atmosphere to a greenhouse kind of condition. So you have a temporary, unstable state where Mars is warmer and has water on the surface.
These small flash floods could be the wet spots that dot the surface of the planet.
It's natural to suspect that maybe this volcanism that has happened in recent history and the water activity are somehow related. But this is one of the mysteries we're trying to investigate, and I think it's one of those that the Phoenix lander may be able to shed some light on.
By finding ice and analyzing its composition, the Phoenix lander is designed to map the planet's ice history. It will tell us how geothermal activity and atmospheric change have affected Mars's ancient water.
Load relief kick crane is in. Vehicles responding. Vehicles Vehicles recovering very nicely from the liftoff transient.
Phoenix's quest represents a journey into the unknown.
Up to now, all of our exploration of Mars has been superficial. We take pictures from orbit, we drive around on the surface, and maybe we dig down this deep, either by dragging it with the wheels or with a little arm or something. We maybe get down this far, and that's it.
But Phoenix is set to change this. It's designed to endure Mars's northern latitudes and to analyze subsurface ice. NASA hopes its findings will throw light on how water interacts with the geology of Mars, the key to unlocking the story of past atmospheric change. In order to achieve this goal, it's been built to do something no other Mars lander has done before.
Phoenix is going to arrive on Mars and land and dig.
A sophisticated robotic arm will dig down 3 feet into the frozen subsurface to where the layer of water is believed to be. At nearly 8 feet, the arm is the most important tool on the lander. It's designed to dig trenches, scrape ice, and deliver samples to other instruments on the lander's deck. No one knows the capability of this arm better than Phoenix's lead scientific investigator, Dr. Peter Smith.
The robotic arm in digging on the surface is doing something very difficult because it's being controlled from 100 million miles away. And so the interaction of using the arm and seeing through the eyes of a camera is not simple. It's like going out to drive a semi-truck with never having driven one before. The truck works, but learning how to shift 18 gears is not so easy.
If working properly, Phoenix's robotic arm will drop ice samples into a device called a Thermal and Evolved Gas Analyzer, or TEGA for short. TEGA has 8 tiny ovens, about the size of an ink cartridge in a ballpoint pen. Not unlike this one. Once a sample is successfully sealed in an oven, the temperature is slowly raised at a constant rate. As the temperature edges up to 1800 degrees Fahrenheit, the ice and other volatile materials in the sample vaporize into a stream of gases.
So if you think about what happens in your kitchen when you put, say, some sort of food in the oven and you start to heat it up, it's cooking nicely at 200, 300, 400 degrees. But if you start to crank that oven up 800, 900 degrees, 1,000 degrees, what's going to happen to the organic materials in there? Well, they're going to turn to smoke. They're going to come out, and like in my kitchen, they're going to set off the smoke alarm. And you're going to be doing an experiment just like TEGA.
Roasting the samples of soil and ice at 1800 degrees releases what are called evolved gases. A mass spectrometer will then scan these gases for minute quantities of hydrogen, oxygen, carbon, and nitrogen, the elements of life. But Phoenix's sophisticated instruments do have a limit. Each of its 8 ovens can be used only once. So as it digs down, it will take samples at 8 different depths. NASA hopes to then map the changing character of the ice. Scientists hope these precise measurements will reveal the evolution of water on the planet and possibly uncover the existence of life. To get a head start on the kind of data the lander might send back, the Phoenix scientists set out to replicate their experiments here on Earth. The geology of Mars and Earth is surprisingly similar. Mars is a cold, dry desert landscape of sand and rocks. But both planets share land features like volcanoes, canyons, and valleys. This is the most Mars-like place on Earth, the Antarctic.
Mars, when it was at its warmest and wettest, would have been like Earth at its coldest and driest. That's why, to me, going to the dry valleys of Antarctica is the next best thing to going to Mars.
Here, Chris McKay and Peter Smith are going to do on Earth what Phoenix will be doing on Mars.
The idea is to make the connection between what Phoenix will measure on Mars with what Phoenix would measure in the dry valleys of Antarctica.
They're digging down to ice to see if life, or the conditions for life, exists in this inhospitable terrain.
We go from a surface soil, which is kind of reddish and definitely of a different character than the lower soils, and we're going to measure layer by layer down to ice. We're using instruments on the deck of the spacecraft, and our robotic arm scoops up samples as it digs down and presents them to the science instruments, which analyze them right there on Mars. I think just by looking at these soils here, you can tell that liquid water's been at work. If we could see that on Mars, we have a place where we have a habitable zone and perhaps a place where life could live.
McKay and Smith's analysis of Antarctic ice reveals that life can exist in the sub-zero temperatures found on Mars.
It's really quite phenomenal what we can find in the dry valleys and in the high Arctic, how life can make do with small, transient amounts of liquid water.
These life forms are called extremophiles. They're microscopic bacteria that thrive in extreme environments. They were first discovered 40 years ago in the 160-degree hot springs of Yellowstone National Park. Since then, others have been found living deep under the ocean, in supersaline environments, even in the uranium-rich pools of water in nuclear power stations. But it's the ones that live in the sub-zero temperatures of Antarctic ice that interest the Phoenix team. They reason that if microbes can be found here, then why not on Mars? So if Phoenix finds ice, it might just find evidence of life locked inside it.
The other remarkable thing about polar deserts is how well ice and cold in general preserves evidence of life. We know that you can go up into permafrost in Siberia and dig out mammoths that have been frozen for 10,000 years or more. On Mars, we're hoping for the same effect. We're hoping to find, frozen in the ice on Mars, evidence of life that may have been preserved maybe for millions, but maybe even also for billions of years. Frozen micro-Martian mammoths, if you will.
Not only will Phoenix detect changes in atmosphere and temperature, it has the ability to identify organics, crucial to the search for life.
Our mission was designed specifically to touch water in the form of ice and to try and understand the properties of that ice, its history, its interaction with the soil, its interaction with the atmosphere, and really explore the question of is there or was there ever life on Mars?
By analyzing the soil samples, Phoenix might finally identify the building blocks of life: carbon, hydrogen, oxygen, and nitrogen on Mars.
And if we saw the organic materials, energy sources, and liquid water present in the past, we would say this is a habitable zone, and perhaps some sort of Martian life could live there.
With the Phoenix mission, NASA's 30-year search for water on Mars could finally come to an end. And by following the water, it might just find life. May 25th, 2008, NASA's Phoenix lander reaches the end of its 9-month-long journey to Mars. It now begins the hunt for life, or at least an environment that could have once supported life. But does NASA really think it can find this on the frozen wastelands of Mars? The answer is yes. This is because of an accidental discovery made by the rover Spirit.
Spirit's most significant scientific discovery came 1,200 days into its 90-day mission.
In 2007, a moving part on Spirit malfunctions. The failure leads to the best evidence yet that Mars was once capable of supporting life.
The right front wheel on Spirit doesn't turn anymore. It's failed. But the one good thing, the silver lining here, is that as we drive and we drag that wheel through the soil, we dig a trench. And every now and then, something interesting will pop up in the bottom of that trench.
X-ray analysis of a patch of soil churned up by the stuck wheel yields unexpected results. It is composed of about 90% pure silica.
That was just a complete unexpected discovery, pure serendipity, and frankly, if the right front wheel had been working properly, we might not have found it.
This $320 million breakdown reveals more evidence of water. On Earth, high levels of silica occur in only two places: hot springs or fumaroles. Both environments bubble with water and life.
The thing that's important about the silica discovery is that you can go to hot springs and you can go to fumaroles on Earth, and in both instances they're teeming with microbial life.
Spirit has discovered evidence of a habitable zone on Mars, a place where extremophiles like those on Earth could have thrived, and may even exist today. What's more, the idea of Martian life is backed up by the 4-billion-year-old Allen Hills meteorite. Structures inside it reveal what some believe is the first real evidence of Martian life forms. David McKay heads the team that made the discovery.
We discovered in Allen Hills what we concluded was strong evidence for past life. That evidence consisted of, number one, some little tiny fossil-like features that are similar to fossils known to occur on Earth. Number two, we found that there were crystals made of an iron oxide, which are also always associated with bacteria on Earth.
McKay and his team believe that the Allen Hills meteorite is proof that life existed on Mars. When they announced their discovery in 1997, most scientists were skeptical.
The discovery of fossils in the Martian meteorite was always problematical. They weren't really biological structures, they were just little round and little oval-shaped things. And people quickly realized that if you pick up any piece of rock or dirt and examine it at that scale, you often see little round and little oval-like structures that have nothing to do with biology.
But Spirit's discovery of silica on Mars has reopened the debate about Martian microbes. If extremophiles can be found in similar environments on Earth, then why not on Mars? Will Phoenix find the evidence that backs up McKay's belief that life existed on Mars? If it does, the implications will be profound.
You may think that if we find life on Mars and it's just microbes, who cares? Why is that important? But within those microbes could be the potential for all of the richness and complexity of life like we see on Earth. In the same sense that an acorn is an oak tree, a single organism on Mars could represent the potential for complex ecosystems for animals and plants and even human-like intelligence. Even if on Mars that seed didn't grow to its full potential, if the acorn didn't become an oak tree, it's still interesting because it tells us that on other worlds, on other stars, it would have fully developed. We're not alone.
It's an astonishing prospect, one that the Phoenix mission is poised to solve.
Well, when Phoenix lands down on Mars and sends back its first signal that it lands successfully, I will breathe a 5-year-long sigh of relief.
But before NASA's latest probe can answer tough questions about life and our place in the universe, it first faces its biggest challenge: descent, and landing. NASA's latest mission to Mars will try to answer some fundamental questions about the red planet and the nature of life in the universe. When Phoenix begins searching ice for traces of life, it takes us closer to understanding our place in the solar system. Is life on Earth a quadrillion to one miracle? Or does it appear wherever and whenever the circumstances are right? Before it can answer these questions, Phoenix has to safely get to Mars. NASA's probe approaches the planet at 74,000 miles per hour.
All stations, Heliocom. At this point, we have a strong signal from Phoenix via Odyssey.
On May 25, 2008, at 7:46 p.m. Eastern Standard Time, the team at JPL begins slowing the spacecraft down for a soft landing on the planet's surface.
It lost the X-band signal from the DSN does indicate an expected cruise stage separation.
This man is responsible for bringing its speed down from 74,000 to 5.5 miles an hour. He's Gentry Lee.
The risky part of the mission begins as we near Mars. When we hit the top of the atmosphere, the process of slowing down begins. And in that 6 to 7 minutes, we slow down from tens of thousands of miles an hour to single digits miles per hour so that we can land softly.
It's a process that involves 3 distinct phases. They're called EDL: entry, descent, and landing. Each is potentially deadly. Friction from the atmosphere slows the craft to about 750 miles per hour.
First, you have a heat shield, which takes this enormous potential energy and converts it into heat. That's 99% of the deceleration. Then when it's done, out pops a parachute, and it takes another 99% of the speed out.
The parachute's performance is crucial to the success of the mission. Up to this point, Phoenix's EDL is identical to any other Mars mission. But unlike the rovers before it, Phoenix has no airbags to cushion its landing. Instead, it uses 12 descent rockets clustered around the hull to slow down. In the final 34 seconds of descent, they fire rapid pulses, carefully timed to bring the lander down at 5.5 miles an hour. If Phoenix's engines fail, its terminal descent will have been just that. For controllers, this is one of many things that could have gone wrong.
And then, of course, will come the moment when it's too late to even ask any questions.
Standing by for possible flashing blackout.
Did the radar see the ground properly? Did the computer interpret the information properly? Did the pulsing engines do what they were supposed to do? I can't wait. Will somebody please tell me now?
On May 25th, 2008, at 7:53 p.m., Phoenix starts its descent.
Ground relative velocity 90 meters per second. Touchdown signal detected. Landing sequence initiated.
The landing is a success. For the team, this is the culmination of 5 years' hard work, and yet the mission is just beginning. These are the first images Phoenix sends back to Earth. The search for life on the red planet begins.